Hi, my name is Ike Ellis, and welcome to Hadoop for the Absolute Beginner. I'm excited to be talking to you today. There's a couple hundred of you online right now, and more signing in as we go. So I'm excited because Developmentor gives a yellow jersey to the people who have the most attendees in their webinars, and I think I'm going to break the record today. So thanks to all of you. I'm a Microsoft Most Valued Professional in SQL Server, and I'm Developmentor's lead SQL course author and lead SQL instructor. I teach the Essential Business Intelligence course and the Essential SQL Server for Developers course, which are both getting a 2014 refresh and will be released soon. So if you need to learn those topics, please think of Developmentor. So today we're going to talk about Hadoop for the Absolute Beginner, and this webinar assumes that you know basically nothing about Hadoop, and maybe you're coming in with a little bit of SQL knowledge or a little bit of data analysis knowledge, but even that isn't super required, so just keep that in mind. We have an hour together, and we'll see how far we get through the agenda. I've got like 40 slides and a bunch of demos, probably 2 hours of content, so excuse me if I speak rather quickly. So for our agenda, we're going to first describe what big data is, which is kind of weird because it's a buzzword and there's a lot of marketing around it, but we're going to talk about the need for big data and why we have a big data problem in our industry today. And then we'll talk about what Hadoop is and why Hadoop helps us solve that problem. And then we'll look closely at the Hadoop ecosystem, which is vast with a lot of different players. There are a lot of different software companies that have Hadoop offerings, and there are a lot of different open source projects around Hadoop. So we'll look at Pig and Hive and Squoop and HCAT, and then we'll look at the future of Hadoop, and we'll look at why Hadoop has a bright future and what the different players are doing to make sure that the future stays vibrant and that Hadoop stays relevant. And then at the end of this, we'll have a Q&A session, and hopefully we'll have enough time for Q&A. So what is big data? Well, big data is what we see on all the marketing literature around any type of company lately, right? We see it like Excel mentions it, right? Like even Office 365 mentions it. Even, ClickView and Tableau mention it. And we see it in IBM literature and in Informatica literature and all sorts of different companies producing it. But what is it really? Wikipedia says that big data is a collection of data sets so large and complex that it becomes difficult to process using on-hand database management tools or traditional data processing applications. So what that means is that big data is generally relative. If you have data coming in that is so large or it's coming in so fast that your existing process can't manage it, that is big data, and that is something that might require a new process or something new to manage it, and that's where Hadoop comes in. So when your existing data processing methodologies are no longer good enough, well look at this is an example data warehouse kind of cube analytics stack, right? This could be any company, but we see Cognos on this label, but really Microsoft has a diagram just like this. Oracle has a diagram just like this. All sorts of different companies. ClickView has a diagram very similar to this. And what you're seeing that we have to take care of like cleaning data and making sure that it's clean and that it's stored somehow. And then once it's stored, we have to worry about aggregating data, whether we do some type of in-memory structure or we put it in an analysis services cube or something like that. And then we have to worry about analyzing data and processing data and then actually asking the question and getting questions answered. Now, I don't know about you, but this stack looks enormously complex to me. Like it is overwhelming. And if you go into like any size company and you say, hey, here's our BI platform that we're going to implement, you could like get lost in this and wonder even where to begin, right? Now, what I want you to do is imagine that you're tackled to say, hey, we've got a ton of data that we need to run through that stack. My question to you is, how long would it take an IT department to go through that stack on a huge amount of data? Would they say, oh, well, we'll have those questions that you have answered in 2 weeks or 2 months or a year, right? It would be, if you said, I want to take every single New York Times article and run it through that stack, clean them up, cube them up, get them ready for analysis. How long would it take to get that done? It would take an incredible amount of time due to the complexity of this. So that is one example of when we might say, wow, our stack is not good enough. It's not fast enough to develop in to get our questions answered. So when we describe the big data characteristics, they talk about the 5 V's, and this is not me making this up. This is very common in big data speak. So you know you have big data if you have volume, a lot of data. If you have velocity, the data needs to be processed very quickly or it's coming in very quickly. You have a variety of data, meaning you have data that might be relational, it might be Excel, it might be CSVs, it might be video, it might be OData feeds. You have variability in the data, which means that as the data matures, the semantics might change, right? Like over time, we might say, well, when we originally started looking at customers, we only wanted their name, address, and phone number, but that was 2 years ago, and now we're getting social security number and driver's license number and a whole bunch of different things. So if there's variability in the semantics, in the meaning or context of the data, then that might be big data. But most importantly, big data has value. There's a question that needs to be answered in a timely manner, and we're trying to process a whole bunch of data, either by volume, velocity, variety, or variability, and the answer is important to us. Okay, so, excuse me. So here's another thing that you might be a little bit concerned about with big data. So in relational data is very structured. Like in typical OLTP applications, you have a customers table, an orders table, they join on a primary key, foreign key relationship, and you might have like 300 tables, and the data types are predictable, right? They're like integers and varchars, string data, and date time and things like that. And relational data does very well when the data is structured, but it doesn't do really well when it's semi-structured, like I'm pouring data in from a log or from GPS coordinates, or I'm just trying to analyze Twitter data, or when it's unstructured, like it's video files or audio files. So if we look at semi-structured or unstructured data and we think, well, how can I put that into my relational data warehouse? That might tell you that maybe the relational data warehouse isn't a good tool for that problem. So let's start at the very beginning. What we do when we analyze data, and it doesn't matter who it is. It doesn't matter if it's my mom trying to figure out her family budget, or if it's some analyst trying to figure out their sales data. When they have like a lot of data, let's just pretend it's in Excel. Let's say that they have 60,000 rows in Excel. The very first thing they're going to do before they analyze it is they're going to clean it. And so they use this existing tool they have to like maybe run macros through it, they clean it, and then they run it through analysis. And that's fine. If you want to clean and analyze it using your existing structures and you can do that, then that's absolutely fine. And so often we just use the tools that we know. We'll use Excel, or we'll use SQL Server integration services or reporting services to clean and to analyze the data. But what happens if it's a ton of data? Like what happens if all of a sudden we want to analyze all the real estate transactions for the US in the last 10 years, or the GPS data for every bike in your bike rental store, or every swing and every pitch in a baseball game, and this data is coming in from a lot of different sources? Now Excel's not good enough, or maybe the Excel process is so cumbersome manually that it just takes too long to get the answers out. Or what happens if the analysis is very complicated? Like tell me when earthquakes are going to happen, or how shoppers view my website, or how to win my next election. By the time we run it through our existing processes, the election might have passed us, or shoppers might already be, leaving the site. So that brings us to SQL Server. And I'm going to talk about this from a SQL Server background because most people who look at development seminars historically have been Microsoft developers, and a lot of you who are here because you know me have SQL backgrounds. So imagine that we have a lot of data, or the analysis is complicated, and we decide, okay, SQL Server is the tool that we're going to use to perform the analysis. So we've got one box here, and we think, man, this data is so huge that we need to make sure that that box can handle it. So we decide we're going to scale up. And what scale up means is that we're going to add RAM, CPU, disk I/O, or network I/O to that box. And that's fine. We can do that. But I promise you, we will hit a wall. We will hit a point where the box can't take any more RAM. It can't take, there's no faster disk I/O. There's no better network I/O. And when we hit that wall, we're going to say to ourselves, well, what do we do next? Well, we need to add SQL servers to the problem. So we're going to scale out. We're going to just keep adding SQL servers over and over and over again until our pain goes away. And that's fine too. We can do that, but there's a tremendous amount of overhead with scaling out relational databases. And most of the time, that overhead is going to happen because of data movement. Like, it's very difficult to keep SQL servers in sync with each other for, like, let's just pretend it's for fault tolerance. Let's say that we're going to add 6 SQL servers to a task. Well, the minute we've added 6 SQL servers to the task, we've increased our point of failure, haven't we? Like, if we're really saying we're going to analyze all the GPS data for all of our bikes and we need this many servers, we probably actually need double 6 servers, right? We need 12, because if one of them fails and the whole thing goes down, we're in a terrible situation, right? Or let's say that we want to segment our data. We want, like, the Seattle GPS data on one server. We want the Portland GPS data on another server. We want the San Diego GPS data on another server. If we do that, there's all kinds of problems related to segmenting data. Like, how do I know I've segmented them evenly? How do I know that inside my segment I have fault tolerance? Once I've segmented it, how do I know that I'm reassembling it correctly? If I do any of this wrong, how do I do any checks to make sure that I know which node gave me bad results, or which node went down, or which node didn't have all the segmented data I thought it had, right? So there's a data movement problem, there's a fault tolerance problem here, and that requires overhead. And the other thing we're going to do is we're going to probably saturate the network. And once we've saturated it, it is very hard to improve network speed. So let's just pretend that we're going to take one large task and break it up into all these smaller tasks for SQL servers. Like, we've kind of already covered it. How do you break them up? Once it's broken up, how do you put them back together again? How do you make sure that your physical data and your computational analysis are broken up appropriately and are broken up in a way that makes sense and are broken up in a similar fashion? And then if we do break things up into these 6 servers, if one server fails, how do we know we need to restart the task, or we need to move over to another node? Or you can kind of get the idea that we are writing a lot of plumbing code. Once we've decided that the data is big enough that we need to break it up into multiple SQL servers, we're going to be handwriting a lot of code that actually has nothing to do with the problem that we're trying to analyze. It's fault tolerance code, it's retry intervals, it's segmenting properly, and at the end of the day, we're actually not adding that much value to our organization. And our organization might be wondering why we're taking so long in order to get this thing accomplished. And in addition, we have one other problem, that is that SQL Server performance doesn't scale in a predictable manner. Meaning, if I have a query over 1 meg of data or a query over 1 terabyte of data, the performance difference between those two queries is significant and somewhat unpredictable. And so because of that, as I scale out to terabytes or maybe even petabytes of data, SQL Server might not even be able to handle petabytes. And if it did handle it over multiple servers, the performance difference might be maybe a deal breaker for the organization. So to summarize and repeat, here's one last thing to talk about the big data problem. We have a problem with drive seek time. There's only so much disk I/O we can get out of one disk, right? There's only so fast we can spin platters. There's only so fast we can swing a swing arm, right? Channel latency has a maximum. Data and processing time is a problem. Network pipe I/O saturation is a problem. There's lots of human problems, like building a data warehouse stack and knowing when to retry when we've split up a problem. And then dealing with semi-structured or unstructured data. All of these things are what I would call big data problems that we need a solution for. And that is why we have Hadoop. Hadoop is not a magic silver bullet that's going to kill all of our problems, but what it is, at its fundamental core, Hadoop is a framework and a set of libraries that handle fault tolerance, logging, data partitioning, and heavy analysis for you in massively parallel problems when you have a ton of data, or you have analysis that's very complicated, or you have a velocity of data that you just can't handle. Then Hadoop gives you a predictable method for taking that huge task and breaking them up into smaller units and then distributing them over commodity hardware. And if you don't remember anything else that I say during this seminar, if you remember that Hadoop handles that, that's probably what you came for. So what is Hadoop? It's a distributed storage and processing technology for large-scale applications, and at its core, it's two different things. It's HDFS, which handles breaking up the data into smaller parts, and it's MapReduce, which handles breaking up processing of the data into smaller parts. So remember, in a big data problem, we have that the data needs to be broken up and the computation portion needs to be broken up. And Hadoop has two different mechanisms for dealing with that. And we'll talk about this more and more, and we'll repeat ourselves more and more as the seminar goes forward. Okay, so Hadoop is open source, which is kind of confusing traditional Microsoft developers. A lot of Microsoft developers are used to kind of like, we go to Microsoft, Microsoft answers our problems, we implement only things from Microsoft, and that's fine. But when you deal with an open source project, you'll see competitors working together, which is new for people with a strong Microsoft background. You'll see a lot of different projects that don't seem to communicate well with each other. And sometimes that happens in Hadoop too. And you'll just see, people that you wouldn't think were releasing projects, like Facebook are releasing projects. Or Yahoo are releasing projects. It also has distributed data replication for fault tolerance. It works on commodity hardware and disparate hardware, meaning not everything in a Hadoop cluster has to be the same. It could be a wide variety of hardware that you have available to you. It handles data and analysis co-location so that it avoids that network saturation problem that you and I talked about earlier. It is scalable in a predictable manner, and it has reliable error handling. So this is a very simplistic idea of the Hadoop ecosystem. This could get a lot more complicated, but because this is Hadoop for the absolute beginner, we're going to keep it simple. So at the bottom, we have HDFS right down here. This is the Hadoop file system, and it's there for storing data. And it could be CSVs, it could be text files, it could be video files, whatever it is. HDFS handles the storage of that data in a distributed fashion. And then over top of that, we have MapReduce, which is the process for processing that data, or querying the data or analyzing the data. Those MapReduce jobs are typically written in Java, but they don't have to be. And then over top of that, we have a layer of abstraction for people that might not want to learn MapReduce, like Pig and Hive and Squoop, that allow us to use MapReduce without kind of getting lost in the complexity and in the details of MapReduce, which can be very difficult very quickly. So under the covers, Hadoop looks like this. Imagine that we have these three servers, which would be a very simple Hadoop cluster. So we have these three servers, and we have these data nodes, one on each server. And these data nodes have some sliced up pieces of data. And the name node right here is a metadata repository for where that data is actually physically stored. And it keeps track of where the data is stored. And then the job tracker is used by MapReduce to submit MapReduce jobs to those exact same servers, those same nodes. So a client job submits a job to the job tracker. The job tracker might use the name node to figure out where the data is, and then break up the job into tasks, and then hand those tasks over to the task tracker, which manages those tasks on the individual servers. Now, what happens is if one of those tasks fails, the job tracker knows that and knows enough about the Hadoop cluster to know, okay, I need to restart that, or I need to move it over to a new node that has the same data, or something like that. So the job tracker is a very, very sharp fellow, and is able to handle redundancy and handle logging and making sure that things are happening and getting returned to the client, in a timely fashion. So take what you know about the Hadoop infrastructure and stop for a second, and let's just talk about basic MapReduce. Now, MapReduce is pretty complicated, and there are a lot of smart people that worked on this. But basically what happens is we're we're taking data and we're reducing it down. We might first take a bunch of data from an input, a whole bunch of data, and then we might just organize it in the right order. And then once we've organized it in the right order, we're going to aggregate it. And then once we've aggregated it, we're going to send it to an output someplace. So pretend it's like this. Like pretend we have this is our input value on the left, and then we're going to our output value on the right. So imagine that we have Joe, subscribes to bank news and auto loan, and Sue does bank news and Sue does account. And what we want to get to is we want to know everything that Joe wants, everything that Sue wants, everything Carlos wants, and Raul wants. Okay, so what do? We take the input values and then we sort them. So we know, okay, Joe's here and Sue's here and Carlos is here. And then we send them over to the reduce jobs to actually do the output to say, okay, single line, we're aggregating it down. Joe wants bank news and auto loan, and Sue wants bank news and accounts. And how that works is like this. So our input could be text files in any order, maybe log files, right? We send them to the mappers. The mappers map them over to the and they call the shuffle and sort kind of the black magic of MapReduce. So the mappers take care of okay, we know that these are the different entities that we care about. Shuffle and sort sorts them in the right order, hands them to the reducers, and then the reducers handle the aggregate. So what are the programming steps? Well, we need to define our inputs, whether or not they're text files, or maybe it's a NoSQL database, or it's Azure Blob Storage. And then we're going to write a map function in Java. And then we write a reduce function in Java, and then we define our outputs, and that could be HDFS or HBase, a NoSQL database, or Azure Blob Storage. And we have a lot of different options for our inputs and outputs, and we actually don't even have to write our MapReduce in Java. We could write them in Python or potentially even .NET. So why do we do this? Well, we do this because Hadoop scales linearly with data size or with analysis complexity, and it can scale to hundreds of petabytes. So when we have these massively parallel problems, we can decide to use Hadoop. And usually we use Hadoop if we're doing machine learning on less than 100 gigs of data, which you would say 100 gigs, I can put that in SQL Server, but perhaps the computational analysis is too severe for SQL Server. Or if we want to do simple SQL queries, like give me every customer I have in Berlin, but I have 100 terabytes of clickstream data to analyze that. So those would be great examples of when to use Hadoop. So in my mind, Hadoop kind of works like this query. Over here at the top, this is just a basic SQL query, right? Give me product name and sum my cost per goods from this table and group by product name. We do this all the time, right? Now, if it's a ton of data or if it's a little data, what we want is we want it to perform about the same. We want it to perform at least in a predictable manner. It might not be fast, but we know that no matter if it's a little data or a lot of data, we're going to get our answer back in 24 hours or 6 hours or however long we think is acceptable. And if it slows down and it gets a little bit lower to run this query, we want to just be able to throw more nodes at it until it speeds up again. So when you think about MapReduce, think about this query at the top. Map is like the group by, where we say, okay, first grab all the product names and put those product names together, and then get them over to the reduce nodes and let the reduce do the aggregate, the sum cost per goods for each product name. So just to refresh, and I know I'm repeating myself, but I'm doing it so that we remember, it's deliberate. Why use Hadoop? We use Hadoop because we don't want to write the plumbing to segment the data, to make jobs redundant and fault tolerant, to overcome job failure or logging. We don't want to have to write all these data providers ourselves. We don't want to have to write providers for CSVs or some NoSQL database or Azure Blob Storage. And then in addition, because people are using Hadoop, all sorts of different people and organizations are releasing scripting languages and tooling and libraries and YouTube videos, and because the framework exists already and everybody's teaching it and everybody is augmenting it, we get a lot of lift from very powerful teams for very little effort. And at its core, it's a scale-free programming model, and that wide adoption is a huge benefit for us. So basically, the reason why we're using Hadoop is because we get to specify the map and reduce functions, and we let the framework do all the heavy work for us without us having to write all of that ourselves. So, and one more time, what's Hadoop good for? It's good for lots of data sets like log analysis. We've talked about clickstream data. Imagine you have 50 web servers and you want to analyze all of the clickstream data from all those logs and figure out like when you're losing users, or when people are getting off of your site, or when they get lost in your site. Maybe we're calculating statistics on enormous data sets, or we're running large simulations like weather simulations, or doing some type of DNA analysis. Or maybe just our ETL is out of control. Maybe we're taking a whole ton of data and we want to pre-aggregate it before we load it in our data warehouse. So we're going to take 5 terabytes and reduce it down to the 5 gigs we actually care about, and then load that 5 gigs into a data warehouse so that we can cube it and run out, maybe more formal and proper analysis on it. We could use it for machine learning or building inverted indexes. Right now, Hadoop has the world record in sorting data. In fact, Hadoop continues to break its own world record for sorting data. We use it for distributed search. We use it for tokenization, taking large amounts of text data or string data and breaking it down into words or phrases to do some type of linguistic research on it. I've heard people say we wanted to do something for plagiarism, and so we used Hadoop for that. Or we wanted to be able to see the most common words in presidential speeches or in newspaper articles, so we used it for that. For large image processing, and because Hadoop doesn't use any fancy hardware, it focuses on commodity hardware, it's very good in the cloud, which is why we have this kind of famous example from Amazon and the New York Times, where the New York Times wanted to process all of their data from every article they've ever published, and they wanted to do basically a word cloud of it. And so they brought up a Hadoop cluster on Amazon for 24 hours, and they did all the processing in a day. And I think at the end of it, it cost them $4,000 in processing fees. I mean, super cheap to get the aggregate that they wanted. Once they had the aggregate, they never had to run it again. And it's an example that they use for Hadoop in a lot of different seminars, and it is a great example of how the cloud and Hadoop can work well together. So what's Hadoop bad for? And Hadoop is bad for things. Like, Hadoop is not a replacement for your relational database system. It's not a replacement when you want the data to be super clean all the time. The latency is too high for an OLTP system. Like, you would never run your CRM product or your customer sales website off of Hadoop. It's not good for sequential algorithms like recursion. So any time where you've got a unit, based on the unit above it, and it has to run sequentially, Hadoop, that's not a great system for a massively parallel system like Hadoop. Not that great for all types of joins. And it's just simply not a good replacement for RDBMS. So don't think of it like that. Think of it as like when the amount of data, the velocity or the volume of the data is too high for the RDBMS, then Hadoop is a good answer for that. So here's a great diagram that I got off the Hortonworks site talking about the differences between relational databases and Hadoop. So this first one is crazy. Like, this is a crazy difference, and a lot of people are going to have a hard time kind of wrapping their minds around it. But in a relational database, you can't write to a relational database without having schema defined, which means that if you and I want to build a relational system, the very first thing we do is we sit in a conference room and we draw out our schema. And then once we've drawn it out, we go in and we create tables, we create foreign keys, we create indexes, we do all that stuff. And then we load that data into the relational database. We insert it, maybe we bulk load it or whatever, right? Hadoop works opposite of that. Hadoop wants the data first, and you can define the schema afterwards. And Hadoop doesn't really care that much about schema, which means that if you have some log files and you put a schema on top of the log files, and I'll show you that in my demo in a second, Hadoop's going to say, well, you've got some entries in the log file that kind of violate your schema, so we'll just skip those. We'll just return nulls on those, right? And that's kind of this powerful thing about Hadoop, which says that the schema can be a little looser, which allows us to not get hung up making sure that everything is perfect by the time it comes time to do our analysis. Speed in relational data, reads are fast, but we always pay a write cost when we make reads fast, and Hadoop writes are fast. Governance, relational data has a lot of standards and structure to it, and if we violate that structure, people get angry. Hadoop is very loosely structured. Processing, it's limited to maybe even no data processing. Hadoop has processing coupled with the data. That we saw that on the job tracker slide, right, where MapReduce was dividing up the jobs to the task managers that were on the nodes that had the data, so they didn't have to move data over the network and saturate the network. Hadoop's good for unstructured data, like we've talked about a couple times already. It's good for scale out, but relational is still the best if you have OLAP analytics or complex asset transactions or an ODS. We still are going to be using the relational databases for those things. And then we'll typically use Hadoop for data discovery, processing unstructured data, and massive storage and processing. So there's another problem, and that is that MapReduce functions are written in like Java or Python or .NET and a few other languages, and those languages are widely known. I mean, if you're a developer, you probably know one of those languages. But the main problem is that analysts and DBAs, the exact people who struggle with big data, are the exact same people that don't know Java or Python. And so, but they do know SQL. They do know how to interact with SQL Server or Oracle or whatever their native SQL language is, or Postgres. And so we have abstractions for MapReduce. We have many of them. I'm going to talk about Pig and Hive, but we have these abstractions that allow people who know SQL but that don't know Java to write MapReduce jobs and still take advantage of Hadoop. So this is what like a typical MapReduce function would look like. So the mapper would say, okay, just break up the words and then hand the words out. And then once the words are all broken up and sorted in the right order, then the reducer would just make a count of every word and say, the word, Main Street in President Obama's speeches exists, 5,000 times or something like that. So what is Pig then? Pig is an abstraction that sits over MapReduce. It's typically used for ETL processes. It looks an awful lot like SQL. It's used for parallel data processing for Hadoop. And I want you to know that I'm not trying to get you to learn Pig. I just want you to want to learn Pig, or to at least think that Pig is worth looking into. It looks SQL-like, but it's a little bit different. In fact, to me, it almost looks a little bit more like LINQ. And it behaves a little bit different than SQL. When you submit SQL to the execution engine in SQL Server, the execution engine takes SQL and then it parses it, it binds it, and then it creates a query plan, and it doesn't really execute it in any specific order. Well, Pig is different than that. Pig absolutely executes in a specific order. In fact, I think Pig behaves a lot like SSIS. And when you see the syntax, you'll kind of see why I say that. But you know how SSIS, this is a typical SSIS data flow going from start to finish, and starts up at the top and finishes down below. And what we're doing is we're taking data from a whole bunch of different data sources, and we're sorting it, and then we're merging it together, and then we're aggregating it, and then we're putting that aggregate down in the output. And that's what Pig is typically doing, is it's grabbing data from data sources, sorting it and messing with it, aggregating it, and then getting it out to the output. So Pig looks like this. So keep in mind that these are actually different Pig commands that are being executed in this one script, and this executes one step at a time. So if we start at the very beginning where we say trx equals, and then we're loading it into, we're loading a table, like we're saying, okay, trx is this transaction and its customer and order amount, and then we're grouping it. We're saying now take trx and group it by customer, and then once we have grouped, take ttl and iterate through grouped and summarize the order amount based on the group. And now cust says, let's load a whole different set of data in here, unrelated to TTL. This is going to be customer and postal code. And then for our result, join the original aggregate that we went through one at a time to get the summarized data and join it to the customer data so that as a result, I get customer, postal code, and the order amount, and then dump the result to the screen. And that executes one thing at a time, very similar to what we said SSIS would do. So how Pig works is Pig Latin goes through a preprocessor. The preprocessor creates the MapReduce jobs, and then the MapReduce jobs get submitted to the job tracker. So Pig is not that complicated and doesn't take that much to learn. It has data types, inputs and outputs, relational operators. It has user-defined functions, scripts, and testing. So here are our data types. We have these very simple scalar data types, ints and longs and doubles and char arrays. And then we have complex data types like a key value pair is called a map. A tuple is a fixed size order collection, and a bag is a collection of tuples. And then we have inputs, like we can grab things from Pig storage or from text loader or from HBase storage, which is a NoSQL iteration for Hadoop. And then so we can load it in that. We can store the data in Pig storage or in HBase storage or in HCatalog, and then we can dump it to the console. So we can either store it to persist it, or we can dump it to the console to just look at it. But be aware you don't want to dump a ton of data to the console, run out of memory. Or not even be able to look at it so much. So we have a lot of relational operators, and a lot of this will be familiar to you, right? If we're going to iterate through a data set, we're going to use for each. We can filter using where, we can group, we can sort. We have distinct to get the unique records coming out. We've got joins. We can do a limit, which is similar to top and SQL. We can randomly sample data. We can specify the level of parallelism on the reducer side, and we can union two data sets together, like the typical Venn diagram unioning. So we can write our own functions in Pig. They're typically written in Java or Python, and we can write functions that do string manipulation or math or complex type of operations. And then here's just some useful commands. Okay, so let's take a look at this. So what you're seeing here in front of you, here's our very first demo. You're seeing Hue, which is the Hadoop user experience, and this is the Hortonworks iteration of Hadoop. So there's three main players in the Hadoop ecosystem. One is Hortonworks, which is the ecosystem that I'm using. There's Cloudera, and then there's MapR. And then there are a lot of partner organizations with those, and Microsoft has partnered strongly with Hortonworks, and other companies have partnered with MapR or Cloudera. So what I'm doing is I'm using a Hortonworks sandbox that I downloaded off the Hortonworks site, and it's pretty easy to do that. You can just, if you just Bing or Google Hortonworks sandbox, you can see that they've created these sandboxes for a lot of different virtualization technologies. Like I'm using Oracle VirtualBox just because it's free, but you can use VMware Fusion, like if you're running a Mac, or you can use Hyper-V, or you can use HDP. But whatever you decide to use, they've got the image for you. You just launch the image, give it enough RAM, and then as soon as you launch it, it says, hey, go to 127.0.0.1.888, and then you'll get to your Hue. And that's what I did, right? Like this is Hue, and you can see 127.0.0.1. I guess I'm on 8,000, and here's my file browser. So you'll see these icons are really helpful. Like we're going to focus on the file browser, on HCat for HCatalog, on Pig, and then a little bit later on Hive. So just a nice little graphical thing. Now you don't have to interact with Pig using Hue, this kind of web tool that I'm using. You can just script it out if you want. You can just go to the command prompt, connect to Hadoop, start issuing Pig commands, and it will work just fine. But I think that it's more accessible to kind of use the GUI and to write our Pig scripts, just right in here. So the very first thing that I'm going to do is I'm just going to load some files into File Browser. So File Browser is my UI over HDFS. Remember, HDFS is used to distribute data across the Hadoop cluster. So if I want to upload a bunch of data, I just say, okay, I do want to upload data. What do I want to upload? Well, I want to upload this batting CSV. So now batting CSV is right here. and I want to upload master CSV. And here's master CSV. And now master CSV is right there. Okay, now those files are now available to use, and they're sitting in HDFS. And so if I go back to Pig and I say, okay, let's go ahead and use that data, here's what it would look like. So this is a quick script. And let's go line by line and talk about what the script does. So this very first script, batting, says load batting CSV and load it into Pig storage with a comma delimiter. And then take runs raw and go through every record in batting. And I want you to know that the first column is player ID, the second column is year, and then the ninth column is runs. And then once you have runs raw, give me every record in runs raw filtered where runs is greater than 0 and make that runs. And then once you have runs, then group runs by year. Okay, so we're going to take all the batting data for Major League Baseball, like how many runs any player made for the last 120 years or so. And then we're going to group it by year. And then we're going to say, give me the maximum person. Show me when they hit the max, who hit the most runs based on year. So iterate through group data that's defined right here, and then generate group as, give me the max as max runs, and we're going to name that variable max runs. So I named all of these things over here on the left side of the equal sign. So once you have that, now create a join max run and join the max runs by runs. So we're going to take the aggregate, join it by runs, and once we have the aggregate, we're doing that so that we get the player ID of who hit the most. And once we have the player ID for who hit the most runs, then dump join data to the console. Now here's the main problem with demoing Hadoop, is that there's this overhead of ripping this out into a MapReduce job, submitting it to the job tracker, and then breaking this apart to the job tracker. And that overhead is like very hard to get around, right? Which is why I have to talk for the 30 seconds or 40 seconds that it takes to run this. So if we were going to do this exact same data, and if it was this low amount of data in SQL Server, the result would come back much more quickly. But the benefit of this is that this will scale in a predictable manner. So this job has ran, and then it's started already, and it's just going to continue to run and log its progress as it goes. And then once the results come back, and hopefully, I'm hoping my fan just kicked on, so Hadoop is working. I gave it plenty of memory, so hopefully it comes back quick. We're going to get the results here, and we're going to be able to look through the player ID, which is kind of a segment of the player name, and figure out who hit the most runs per year, who our run leaders were. Not home run, just run. While we're doing that, we can kind of take a look at the player data if you'd like to see where we started with. That batting CSV looks like this. So we get this player ID, we get the years that they were active, and we have all sorts of batting data for them, including how many home runs they had, how many RBIs they had, and finally what we're interested in, how many runs they scored. By the way, I apologize for any of the non-US people who might have joined the webinar today, because we are using American baseball. So, but runs are, not to be blasphemous to baseball aficionados, but runs are points in baseball, although you're not supposed to call them points. That's considered heretical. But okay, let's see. You get this like barber pole that kind of runs forward and gives you a false sense of security that things are running fast. What I should have done is I should have executed it and then explained it while it was executing. Oh, but while we do that, look at Pig Helper. So as you pull down Pig Helper, if you wanted to know what Pig has to offer you, like how to load files or dump things back into storage, you can just click on Pig Helper, and it will put these statements into your script, and then you just fill in the missing variables, so you can kind of see what functions Pig has available to you. All right, I think we're almost done here. And then we'll go on to Hive. All right, so 1871. Well, I don't know if you guys knew who Eagle was and why he had 94 runs scored, or who Hamel was and why he had 192. Those are 100 years ago. Most people don't know. But if we go to the end of the data set, we know Curtis Granderson scored 134 runs, or some of these we know Grady Sizemore, we know Albert Pujols, right? We know Alphonse Soriano, we know Sammy Sosa. Now we're getting into names that we know, and we're getting into numbers that feel comfortable for us. And probably if we hit the middle of the data set, we would probably know Ty Cobb, right? And we would know Babe Ruth and things like that. So we recognize this data, and we got the results coming back to us. And this syntax isn't complicated, right? Doesn't this make Hadoop accessible for you? Don't you feel a lot more comfortable with Hadoop knowing that Pig is available for you, and that this SQL-like syntax exists and it's learnable? It's not that hard. Okay. So now that you've seen Pig, let's take a look at Hive. So if Pig is used primarily for ETL, although it doesn't have to be, but that's primarily why it's used, Hive is used as a query language to actually get data out so that we can look at it and analyze it. And it looks an awful lot like SQL. In fact, it's based on the SQL 92 standard. So it's SQL versus Hive. It's almost useless to compare the two because they're so similar. But when you create a table in Hive, you actually consume the data and you store it. So Hive is more like, maybe I should tell you something about tell you something about Pig. In Pig right here, once the script is done, these data structures go away. Nothing here is persisting unless I tell Pig to persist. So once I dumped it and you saw the results here, done. If I want to look at the exact same data again, I need to run Pig again and do the whole script again, unless I specifically go to like these storage helpers and say, okay, store it into hcatalog or store it into HDFS, and then I can use the results from my storage place, right? But Hive doesn't work that way. Hive is meant to put a schema over existing files, consume those files, and then persist them, and then let you query them like you would query any table, and query them repeatedly, and do repeated analysis, and dig deeper into the data, and do whatever you want with Hive. So it's going to feel more comfortable to you for those of you who are used to like creating tables and querying them inside SQL. But don't throw out SQL, because Hive is really good for batch processing large data sets on hundreds or even thousands of machines, up to 4,000 machines. Hive has high overhead when starting a job because it also has to translate its queries into MapReduce. Hive does not cache data. Hive performance tuning is mainly Hadoop performance tuning. And there's a similarity in the query engine, but they are different architectures for different purposes. So don't think of Hive as a replacement for OLTP workloads. So Hive components, we have data types that look like this. Here are our scalars, and we have more complex data types like structs and arrays. We can create a database, like create new database in HDFS, call it new DB. We can create tables. Those tables can have columns. Those columns have data types like you're used to seeing. Data can be added and removed independently, which is very powerful for Hive. And then Hive is a translation tool. I'm kind of going fast because I realize I'm running out of time. So Hive is a translation tool. It takes that SQL query and translates it over to a MapReduce job. It's a structuring tool because it allows us to place a schema over top of HDFS or HBase. Hive tables have rows and columns. There's a metastore, and it works with a different metastore, which I'm trying to show you in just a second. This is how you define a Hive table. You create table, the name of the table, the column names, and then you say, okay, it's going to be this text file. Consume this text file to create it. And then you can load data into the table that you just created. And then you query it using select, using very common select statements like a select from, group, join, all the things that you would expect to have in a select query. You can use an order by. And so here's a Hive demo. So this was Pig right here, Pig, and Hive is the little b right here. So let's do this thing. So first off, notice that inside Hive, I don't have any tables here, right? No tables at all. And notice in my file browser, I still have batting CSV and matter CSV. So when Pig used these things, when it used batting CSV, it just loaded it into memory, used it, gave you the aggregate, and was done, and left the file alone. Watch what happens when we're in Hive. So just to kind of highlight the differences. So the first thing that we're going to do is we're just going to create a table. So create table batting, player ID as string, year as int, runs as int. Now, anybody who's done SQL recognizes this syntax. This is just standard SQL syntax, and we'll execute that, and we'll create the batting table. And then once we have that, let's load it from our file. So, all right. So now, by the way, let's look at tables. There's the batting table right there. Here are the columns that I created. If I browse the data, no data, right? No data yet, but there's a schema sitting right there ready to be used. So now what I'm going to do is I'm going to overwrite the table batting that I just created, and I'm going to take this regex for player ID, year, and run from temp batting. Now here's the thing. I don't have temp batting created quite yet. So in order to create temp batting, what I'm going to first do is go into tables, and I'm going to create a new table from a file. And then under table name, I'm going to call it temp batting. And then the input, the file name, I'm just going to take that batting CSV. And now it took a look inside batting CSV, and then it found a whole bunch of columns here, right? And I can take a look at all these columns, and let's see. Actually, let's go back to choosing a file real quick. Temp batting, input file. Yep. Okay, so that's one way that I can create the table here, but I actually am going to do it through syntax. So I'm not actually going to click next right here. Instead, I'm going to go back to my query editor, and I'm going to load the data from batting CSV into the table temp batting. And let's execute that and load it. Uh-oh. I got an error. Let's see what the error is. Let's make sure that the file is there. There's batting CSV. Is that file in the right place? Let's see. So if I look at batting CSV, it's under Hue, and if I click on it, it shows me that it's user Hue batting CSV. So that's user Hue batting CSV overwrite into table temp batting, which should work. Let's see. Uh-oh. Maybe what I should do is just bring it in from the file. So temp batting, input file will be batting CSV. Do next, comma delimit it. That's fine, except I don't like these column names. Let's see. Okay, so I can change my column names. Like this one could be player ID, and then this one can be year ID. And then over here, we want the R to be runs. That column 8. Same thing that I did before, right? Create the table. Okay, once that table is created, you see all the columns here. You see player ID, runs, and year ID. And if I go to File Browser, notice that that batting CSV has now been consumed. It's not like Pig, where Pig just put the schema over the CSV. It actually took the file and created a table off of the file. Okay, let's see if I can run that load command and overwrite an temp batting again and see if it, no, it's going to error out. All right, I don't know why. Okay, so now what we can do is go back to that table. We can see temp batting. We can see the schema, and we can actually browse the data and see the data in it, right? We can see, you think this is Hank Aaron? No, that's not Hank Aaron because it's 2004. I don't know who that is. But you'll see kind of, maybe if you're a bigger baseball fan than I am, you'll see familiar names here, and you'll see the years they played, and you'll see the stats for those years. So now let's try to to load that batting table from temp batting. I'm erroring out today, and I don't know why. I just ran all of my demos, nothing errored, and then in real life, I get errors, and I'm not sure why. So it's probably not parsing correctly. I wonder if what I can do, I'm just going to solve it real quick. Let me go ahead and drop this real quick. Let me load up the batting file one more time. So here's batting. And then let's go back, go to tables, create a new table from file. Let's just call it temp batting. Let's go back to batting CSV. Let's not rename anything right here. Create the table. Okay, consume it. And let's try to insert. No, it's not going to let me. You guys, I'm sorry that the Hive demo isn't working right. But okay, let's take a look at what a Hive query looks like just so that we can get a sense of it. So these are two different Hive queries. And if the data loaded correctly, and I don't want to go through logs right now, and unfortunately Hadoop takes too long for me to parse through the log and figure out what I did wrong. But if I take the batting data, I can group it by year. Look, this is standard SQL, right? You guys know this. You guys know group by year, max run. So that's one way, right? Here's another way. This is me taking a subquery, just like you guys know and love subqueries, and then aliasing it, and then joining that subquery alias on year and on runs, and then querying and getting the results back. And the results come back in a tabular form, and you can, just once the table's been created and once it's persisted, you can run any type of query that you want against it and continue to do your analysis on it. Okay, so real quick, let's go back to the slides because I've got some more to cover. So Pig versus Hive. So there's a famous Yahoo blog post on Pig versus Hive, and you can look at that. This is just to kind of show you that blog post. He does a great job. This is one of the founding members of the Hadoop team on the Hive stack. I think it might have been on the Hive stack. So, but he does a great job of explaining what Pig and Hive are, why they're used, and why Yahoo chose to implement both of them. He wrote this like a few years ago. I think this was written, 2010, and it's just as pertinent today. So it's in my slide deck, and you're welcome to kind of peruse that article as a good refresher. So remember that Pig is primarily used for ETL. It's good for aggregating data and putting the results so you can do something with it, like storing it in an RDBMS or storing it someplace else. Good for SQL authors. And then Hive is good for analysis. It's also good for SQL authors, and it can also be used in Excel. You can use an Excel driver and just submit SQL statements against Hadoop using Hive and then get the results back and do any kind of analysis on it. Microsoft has all kinds of demos on how to do that. Another tool is Squoop. This is an ETL tool for getting data in and out of an RDBMS. So we can import from an RDBMS into HFDS, or we can go, HDFS, or we can go from HDFS into the RDBMS. You saw Who. Hue is the Hadoop user experience. That's that website that I was using. Okay, hcatalog is interesting, and because I've only got a few minutes left, imagine that we have a lot of different data stores down here below. We have HBase, which is that NoSQL implementation for Hadoop. We have HDFS, which are the text files you saw me play with, and maybe additional databases in the future. And then at the top, we have different people that are consuming those resources. We have MapReduce jobs, Pig, Hive, there's all sorts of different mechanisms could be using that data. What hcatalog does is it provides a consistent schema for all of those components. So hcatalog lets us create tables and columns, and those mechanisms that can use hcatalog can take advantage of Hadoop and of the same schema. So when we do work on making the schema right in one place, that work can be reused in a lot of different places, and that schema can be over a lot of different data sources. So what you're doing in hcatalog is you're actually creating tables that can be used by other people. And we have it so that different tooling that have different data types can kind of come to an agreement on how data is stored and what data types we're going to actually be using. So the way it works is, if we go back to hue and go to HCat, look, I've got batting and temp batting already in HCat, right? And I can browse the data here. No data yet. Or here's temp batting. We know that has data, right? Okay. And then I can create a new database if I want, or I can create new tables if I want. So same thing, create the new table from a file, right? The way that you saw me do it before. And then once the table is created there, it can be consumed. So, just kind of like what you saw me do before, where I created the table based on a file, based on like master CSV or batting CSV. Once it's defined, once you create the schema, like once you specify the columns and the column data types, then you can query from it. And you can say things like, here, let's try it here for a second. So let's upload batting CSV again. Okay, and then let's go to hcatalog, and let's create a new table from file, and we'll just call it batting underscore hcatalog, and then we'll take batting, and okay, so that's the table name, that's the input file, it's comma delimited, player ID, year ID, right, just like we kind of wanted from before, and then remember, we don't want R. We actually want to be more descriptive than that. We want runs. And then we create the table. And so once we have this table, batting HCat, in hcatalog, we can consume it in either Pig or in Hive. So it imports, and hopefully it's done in a second. And then to consume it, it would just look like a straight select star command. So it would just be like select star from that table name, batting HCat. Oh, look, and data coming back out for us. So once you're in Hive, you can do anything that you'd like to do as far as joining or querying on different data. I don't have a lot of different. Let's see, we can run this query maybe. No, I don't have master data loaded in yet. Or if we just wanted to see the schema, we can just do a describe command. Uh-oh. It is describe HCat, right? Not data, but HCat. And then execute that. And then there's the schema coming back according to Hive, even though that's an HCat table. And like I said, we can consume that in Pig as well. Okay, what else? HBase is the NoSQL database. So Yarn is the next version of Hadoop. Sometimes this is called MapReduce 2.0. The reason why we have Yarn, it stands for Yet Another Resource Negotiator, is that MapReduce was too big of a player in the first versions of Hadoop. And what they found is that they wanted to get these massively parallel problems that MapReduce didn't necessarily fit well into. So they wanted to be able to take graph databases or in-memory structures and massively parallelize them, and MapReduce wasn't doing a great job of that. So what Yarn does is it takes MapReduce and it reduces it to a module inside Yarn so that we can plug in a bunch of different modules in Yarn. And one that's gaining a lot of traction right now is Spark, which is the in-memory module for Hadoop, but there are others as well. And this is just came out last June and is getting a lot of traction right now. Impala is for real-time queries and real-time analytics that Cloudera has made. That's kind of vendor-specific. Storm is the open source equivalent of what Impala is. And then here are the players and people that are having Hadoop offerings and that are currently playing in the ecosystem. So in my opinion, I think Hadoop has a bright future. I think that A lot of players are giving it vibrancy. They're competing with each other. They're trying to push the envelope. We're seeing a lot of RDBMS features push into Hadoop, and we're seeing Hadoop features push into the RDBMS. So there's going to be some overlap and maybe cause some more confusion, but I think that there's a bright future for both. We've got a lot of third-party vendors coming in, lots of buy-in, lots of progress, lots of changes. It's almost a full-time job to keep track of all the Hadoop changes that are coming out and to know, who's doing what and why they're doing it. If you want to learn more about Hadoop, we're thinking about a course that we're writing right now. Michael Kennedy and I are considering writing, and we're hopefully we'll have that course released. I couldn't give you a time, but sooner the better. You can also read Hadoop, the Definitive Guide, and if you guys are SQL professionals, you can look at the SQL Pass book readers. So this is a book club, and we meet once a month, and we're actually meeting tomorrow. And right now, we're reading Hadoop, the Definitive Guide. You just have to buy the book and read chapters 4, 5, and 6, and then meet with us tomorrow, February 19th, for an hour. A bunch of other MVPs and I get together, Ike, Brad, Rob, Scott, get together, and we just talk about what we read and kind of make the book a little bit more accessible for everybody. So that's it, you guys. I hope you enjoyed Hadoop for the absolute beginner, and keep in touch. If you have any questions or you want to get a hold of me, that's more about me. I'm actually the chairman for the SQL Pass book readers, and I'm active in SQL Pass, and I respond on Twitter, and you can email me if you want. It's just Ike at ikeellis.com, and thanks a lot.